Alright, welcome to class today. I am away for one last day, so we'll do one more video lecture. Again, I thank our TA Nathan and my graduate student Pierre for helping out today. And I should be back on Tuesday. Alright, so today we are going to cover, we're going to talk about ODEs again. So this is lecture 15. Numerical ODEs. Okay, and if you haven't already, please pause. We should have prayer today and a spiritual thought. So if you haven't done that, please go ahead and pause. Okay, so for our unit of the day today, I am going to cover one that I noticed in the review that we had missed that I think would be a great one to do. So we're going to talk about the conversion between degrees Fahrenheit and degrees Celsius. Okay, and so the conversion there is 9/5 times degrees Celsius. You have to add 32. Okay, so that's the unit of the day, conversion between degrees Fahrenheit and degrees Celsius. Okay. So let's talk a little bit about ODEs. So I'm going to label this section Systems of Rate Equations. Okay, and we're going to start out with a little bit of a review. Okay, so during our Excel unit we talked about rate equations. Okay, and what we said was a rate equation. Let me scroll down a little bit here. We said a rate equation had the following form. A rate equation was dy dt equals some function of y and t. Okay? And it also had some initial condition, y at 0 is equal to y naught. Okay? And we said that to be a rate equation, under our definition, this had to be first order. Okay? Which meant that they're only first derivatives. Okay? Okay? Then we also said that it had to be an ordinary differential equation. Ordinary differential equation. Okay? Which meant that it only had derivatives with respect to one dependent variable, namely t. Okay? So we didn't have, let me erase that real quick. We didn't have partial derivatives. Okay, no d dx, d dy, etc. Okay, we didn't have those. So it's an ordinary differential equation. Okay, and then the last thing that we said was, pardon me, lost my mouse there for a second. Okay, we said that it was an IVP, an initial value problem. Okay, and what we mean by that is that we know y at 0, okay, as opposed to something else. And we won't talk about boundary value problems, so you can just leave it at that. Okay, and what we said was that in your ODEs class that you're either concurrently taking or you will take, or maybe you've taken, you're going to talk about solving differential equations analytically. Okay, so you'll learn about how to do this analytically. And we care about this numerically. Okay, and so I just wanted to make a couple comments about this. Okay, so the first thing I wanted to say, so we just did integration. So I wanted to point out sometimes people get integration, okay, confused with solving a differential equation. Okay, so integration is not the same thing, okay, as solving an ODE. Okay. In general, solving an ODE is harder. Okay. This one is harder. Okay, than integration. Okay. Sometimes solving an ODE reduces to the case of an integration. In certain cases, okay, it will just be an integral. But in general, it's harder. Okay. So that's maybe the first thing to say. And I wanted to remind us we had derived a method. Okay, a simple method. There are many, but we just did a simple one for solving, I guess I'll put method of solution. Okay, and this was the explicit Euler. Explicit Euler. Okay, and the explicit Euler method looked like the following. We had y at n plus 1 time point. It's going to be y at the n time point plus delta t times f of y of n t of n. Okay, and that's the explicit Euler. And then we also had to, of course, know the initial condition. Okay? All right. So what I want to talk today is I want to talk a little bit more about systems of rate equations. So this was all for a single equation, and we briefly talked about systems of equations, but I want to go in a little bit more depth here about systems. Okay, so what is a system? Well, just like the case of, let me just write systems of rate equations. Okay, and just like the case with nonlinear equations, this just means we have many of them. Okay, so we can have d1 dt is f1 of y1, y2, yn. dy2 dt is f2 of y1, y2, yn. Oh, and I forgot, over here there should also be comma t. So it can also depend on t. Comma t. Okay? And then we can have many of these equations all the way until dym dt is fm of y1, y2, ... ymt. I forgot, these shouldn't be n's, these should be m's. Okay? So what I mean by m is the number of equations and the number of y's. Okay, and then n, which is what I used up here, that'll be the number of time points. Okay? Okay, and with these rate equations then, we should also have some initial conditions. Okay, so we need to have an initial condition for every one. So we're going to have y1 at 0 equals y1, 0. y2 at 0 is y2, 0. Down to ym at 0 equals ym, 0. Okay? So that's a system of equations. Okay? And if you remember when we talked about nonlinear equations, we said that a system, okay, we have a system, and the system could be linear or nonlinear. Okay? Or it could be coupled or uncoupled. So just to remind ourselves what that meant, okay, linear is something, there's a precise definition, and we won't spend the time to go over that, but essentially it's something where we don't have things like y squared or natural log y or y1 times y2. Okay, these are all nonlinear terms. Okay, so we have something that looks like dy dt is like y, okay, just something simple y, something like that, okay, but it can have parts of t that are nonlinear, okay, so t squared or log t or ty, okay, that's all okay for linear. That's still linear, okay, and why that is I'm just not going to go into. So it's just something to remember. Okay, so if you have something like this and you have some, so long as it's linear in the y's, it's linear. Okay, and then coupled just means that you have something where equations depend on each other. Okay, so coupled, an example of that would be, dy1 dt is equal to minus y2, and dy2 dt is equal to minus y1. Okay, they depend on each other. You can't solve them independent of each other. Okay, so that's linear and nonlinear and coupled. Okay, to remind ourselves of that. Okay, and we can also we can do explicit Euler. Okay, in a system. It's kind of terrible handwriting. Apologize. Oh, I need to do that. dy dt. Just erase this. Okay, in a system. Okay, and it looks the same if we use vector notation. So in vector notation, we have y n plus 1. Okay, these are now time points. As y at n plus delta t f vector y n t n. Okay, and we can write this out. Write it all out. Okay, to see all the different components of those vectors. So we'd have y1 n plus 1 is y1 at n plus delta t f y1 n y2 n dot 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 tn. Okay, and then we could have y2 at n plus 1 is y2 at n plus delta t f y1 at n, y2 at n, dot 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 tn. Okay, and all the way down until we had ym at n plus 1 is ym at n plus delta t f y1 at n, y2 at n, not plus, comma, dot 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 t at n. Okay? So that's writing that all out. Okay, so the explicit Euler still applies. Okay, so the last idea to talk about with systems of equations is what happens if we have higher order ODEs. Okay, so by that I mean what happens if we have, for example, a second derivative. Okay, and you might be thinking, Dr. Tree, you just said that we weren't going to do second derivatives. We limited our rate equations to first derivatives. Okay, and what I'm going to show you is that we can turn any higher order ODE into a system of first order ODEs. Okay, so we're going to turn higher order ODEs, we're going to turn into a system of first order ODEs. Okay, and with this second derivative, we're going to have an initial condition y at 0 is equal to y0, and we're also going to be given an initial condition for the derivative. Okay, t equals 0 equals, we're going to call that v0 for now. Okay, oh, my writing's starting to go a little sideways. Sorry about that. Okay, so how do we do this? Well, it's pretty simple. Once you know what to do. Okay, the basic gist is that you make a substitution, okay, for a derivative. Okay, so if I make the substitution for v for this derivative here, now I made up that variable. Okay, and v is nice, it's the velocity, right, if this were a position. Okay, so this is just something we define. Okay, and then I go back to my initial equation here, and I say, well, dy or d2y dt squared, okay, is the same as the derivative, oops, not with respect to y, with respect to t, okay, of dy dt. Okay, but dy dt I said was v, so that's just d dt of v, or dv dt. That's a first derivative. Okay, so I can take that. Oh, let's try and keep my other equation up there. Now I have an equation that says dv dt equals minus gt. That's one equation. And I have another equation that says dy dt equals v. That's two equations. I just turned a second order equation to two first order equations. Okay? And then I can use the initial conditions. I know that y at 0 is equal to y0. And I know over here that dy dt, which is equal to v at 0 is equal to v0. Okay, so there I also have the initial conditions that go with it. Okay, so I took a second order ODE and I turned it into a system of first order ODEs. Okay, or rate. These are what I called rate equations. Okay, so that's great. And it turns out this is general. That the same thing that we did, okay, here, where we made this substitution, okay, where I did right here, where I made a substitution for the derivative. That's it. That's the key. Okay, that's all I have to do right there, no matter what the equation is. Okay, so the steps are to doing this. I'll just write out what the steps are. Steps. Okay. 1. It's define a new variable, okay, for each derivative, for each order of derivative. Okay, so for example, let me just show you third order to maybe make it a little more concrete. If I have a third order derivative, I can say that v is equal to dy dt, okay, and then I can say a is equal to dv dt. Okay, and if I do that, if I have d cubed y dt cubed, that's equal to d dt of y dt. Okay, so that's going to equal dA dt. Okay, so anywhere where I had a third derivative, I'm now going to have a derivative of a, okay, because that one is d squared y dt squared, the second derivative of y. Okay, and anywhere where I had something that has second derivative, I have v, and that's it. That's all I have to do. Okay, I just keep adding variables for every order of derivative that I go up. Okay, so that's step 1. Okay, step 2 is substitute my definition, okay, into the original ODE. Okay, that's step 2. I sort of showed you step 2, right? I substituted there, okay, and then I would substitute in whatever original ODE I had. Okay, 3 is find the initial conditions. Okay, and then 4 would be solve the system. Okay, say using explicit Euler. Okay, so now you have about 7 minutes or so to practice, and I have some practice, just some qualitative problems, and I'll just show you what they look like so you can find them. They're on the web. Okay, they look like this. The sheet looks like this. Okay, it says lecture 4. It should be lecture 15. I'll fix that. Practice problem number 1. Okay, and it has some equations for you to classify, and then an equation for you to rearrange. Okay, and substitute and practice with that. All right, so I'll go ahead and pause the video and do that practice. Okay, so you should have done that practice, and hopefully that was useful. With the remainder of our time, I'm going to go over the ODE solvers in Python. How do we solve individual ODEs and systems of ODEs in Python? And fortunately for us, we don't have to just use explicit Euler like we did in Excel. There's a whole host of pre-written functions that are available to us. Okay, so that will be, here we go, starting on section 2. Okay, ODE solvers in Python. Okay, so the ODE solvers, okay, okay, they live in the same module as the integrate. So they live in scipy.integrate. Okay, so if you remember, this is where we had quad and simps. Okay, And the one that we're going to use, okay, that's the most useful to us, is called ODEint. Okay, so ODEint, int. Okay, this is in general much more accurate, okay, than explicit Euler. The default method here is I'll just tell you what it is. I don't expect you to remember this, but it's called a Runge Kutta 4-5 method. Okay, the 4-5 being it's a fourth order accurate. It turns out this explicit Euler is only a first order accurate. Okay, and I guess we haven't talked about that. I don't expect you to remember that, but you may hear that at some point. Okay, so in connection with these ODE solvers, we have an example sheet, okay, where I'm going to show you how to do the syntax, okay, and how to use. Okay, and then of course we also have a practice problem, okay, which we'll do at the end. Okay, and this is going to conclude my sort of lecture notes. I'm going to flip over to Spider and show you how to use the syntax on these guys. So let's see, the example ODE solver. Okay, so here we go. This is our example of the ODE solvers. And again, I provide a link to the scipy.integrate module and identify that it's ODEint that we care about. Okay, so what are the steps involved? So like all of these lately, the first step is to import ODEint from the scipy.integrate module. Okay, the second step is to define a function. Okay, and this is the function that we're going to use. And what we need to do is make sure that this function is in the standard form. Okay, so what I mean by standard form, I guess I'll go back to my notes here just to make sure. What I mean by the standard form is that we have dy dt is equal to f of y comma t. Okay, and these could of course be vectors. Okay, and so the function I'm defining is this function. Okay, it's the right hand side function. Okay, that's what I mean by that. So we want to make sure that we define that function in its standard form, and the arguments of the function are going to be y comma t comma other optional arguments that are parameters. So when we talked about nonlinear equations, we also had a form like this. We had y, we didn't have a t, and then we had optional other arguments. So the third step will be to create an array of times. So I'll show you what that is, but that will just be a linearly spaced array most often. So 0, 0.1, 0.2, 0.3, etc. We'll create the whole array of all the times. Then we need to set the initial condition. And the last step here is to call ODEint to find the solution. The ODEint, it takes the function name as its first parameter, the initial condition as the second parameter, the array of times that we created in step 3 as the third parameter, and then if I can scroll over here, it takes other arguments that you might add, which were on the right handmost arguments to the function, if you put args equals, some tuple that has those arguments in it. Okay? And then this here just describes what I just told you. And then the solution, the ODEint returns the solution and also returns extra information if you want it. Okay, so an example. The example we're going to do is to solve this differential equation, which is dc dt equals minus c over tau. And we're going to assume, let me delete these extra formatting terms here. We're going to use the parameter tau equals 1. We're going to use the initial condition c is initially equal to 0, or excuse me, initially equal to 1. And then we're going to go from 0 to the final time, which is 5. So we go through our steps here. Step 1 import ODEint from scipy.integrate. So from scipy.integrate, import ODEint. The second step is to define the function. So we're going to define the right-hand side function, c comma t. And we define tau to be 1, and then we just return minus c over tau, which is exactly what this is, the right-hand side function. Step 3, we create an array of times that we want to get the solution at. So here we'll create a time between 0 and 5, and we're going to create 20 time points. So those are the times we're going to create. We set our initial condition, c0 equal to 1, and the last thing we do is we solve the problem by calling ODEint, right-hand side function, comma, initial condition, comma, times. Okay, and we give it c. And it looks like I was mistaken here. I think this is an optional return, so I'm just going to delete that. So it returns the solution. It can return info. This is optional. So sorry about that initial confusion. Okay, and then what I'm going to do is plot this. So I'm going to plot the times versus, and this is the exact solution. So this ODE turns out is pretty simple. This is one of the cases where we can integrate. So the derivative is just equal to something. If we separate, we divide by c on both sides, then we can integrate both sides and we can find the answer. And that's how we find this, okay, that it's a decaying exponential. And we're going to compare our answer to the exact answer and see what the differential equation gives. Okay, so I ran it, and now I can pull up the plot, and here's the plot right here. And we see that we get an exponential decay starting at time equals 0, and our ODEint lines up very well with our exact. Okay, so because I mentioned up here that you could have extra arguments, I also included an example with extra arguments where I include tau here as an extra argument. And it solves the previous example where you change tau between 1, 2, and 3. I won't go over that in detail, but you can look at that at your own time if you're interested. The last one that I'm going to cover is systems of equations. So if we have a system of equations where we have multiple unknowns, we do the problem in a very similar way, but we use an array in the function that we defined instead of just a single variable. And if you recall, a few lectures ago we talked about fsolve, and we said fsolve had this function, and there was a variable that was an array that we used to hold different variables in it, right? Array is the, this Y array is like an ice cube tray, and it has different locations for different variables, and so that's what we did there. And we do the same thing here. Okay, we pass in just a single array that will hold the different values of y that we want to hold. Okay, so the only difference between solving a system of equations and solving a single equation is to make sure that we do this as an array. So for an example, I'm going to do something where we have two rate equation of two equations here. We have dv dt is equal to g minus cv squared, and dx dt is equal to v. So this is the velocity of some falling object, where x is the position and v is the velocity. G is the gravitational constant, and c is a drag coefficient. We're going to integrate this starting at v equals 0 and x equals 0, and we'll have t at the end be equal to 2. Okay, so the first thing we need to do before we do any of these other previous steps is we need to write this in the standard form, where we write it as dy0 dt and dy1 dt is equal to f0 and f1 respectively. So to do that, we make the substitution that y0 is equal to v and y1 is equal to x. So that will go right here. And then f0 is going to equal g minus c y0 squared, since y0 is v. And f1 is going to equal y0, since y0 is still v. Okay, so now what we do is we've already imported ODEint, so we don't need to import it again because we did that above. Now we define the function f, and I called this fc just because we're in part C of this sheet here. And I define v as y0 and x as y1. I define g as 9.81, which is a constant, and c as 1. Both of these were given. And then I define the functions dv dt is equal to g minus cv squared, and dx dt is equal to v. And then I return an array. So note that what came in y was an array, and what I return is an array. And the array is, and the order is the same. So whereas y0 was v, dv dt is the equation 0, and this is equation 1. So I return an array of those two equations. Then I do step 3. I set up the times, which I'm going to do here from 0 to 2 and have 100 time points. Step 4 is to set the initial condition. Note that the initial condition is an array. So I have v here and x here. And then 5, I find the solution by running ODEint. So y is assigned to ODEint, where I give it the function, the initial condition, and the set of times. And then this will run, and finally I'll make a plot, and I'm going to plot the times versus y, and this will give me the 0 element of y. Okay, so this will be all of the rows and the first column, and this will be all of the rows and the second column, okay, of this y array that gets returned. And so this will be the velocities, and this will be the positions. Okay, so I can run this and look at it, and indeed that's what we see. We see that the velocity starts out, and this falling object, I start to accelerate, and over time what happens is my speed goes up, so my total drag goes up, and my velocity levels off, and I come to a terminal velocity, and my x, my position with time, just keeps going and going and going. So initially it starts out slow, but it goes pretty fast, and eventually it has a constant slope because my velocity is a constant. All right, so those are the practices, that's the examples of how we use the ODE solver. You have a practice problem using chemical reaction with 4 different components, A, B, C, and D. You can go ahead and do this practice problem. The TA, Nathan and Pierre should be able to go around and help you work on this problem. And as always, the practice problem is the first problem on your homework, so if you get that done, please go ahead and proceed to finishing your homework assignment. I will be available by email if you have questions, and hopefully we'll see you on Tuesday. Have a good one.